Okay, next one is going to be the what do we get if we want to do the differentiation with respect to psi of your Fourier transform. Okay, so you've got your Fourier transform and you want to take its derivative. So let's see what it gives us. All right, so let's do the differentiation with respect to psi. So let's assume you have computed the Fourier transform of some function. That's going to be a function of psi, so that should be equal to the integral on R of f of x. I left some room before my integral because you see I'm going to apply differentiation. Okay, so as I said, I want to compute the derivative of this thing, so that's a function of psi, so d over d psi of that whole thing. Well, the good news is that, well, you have an idea of what's happening here, because what we want is to differentiate this parameter-dependent integral with respect to the parameter. And you know some conditions about that. The first condition, actually, well, apart from existence of the integral, is that we need that the derivative with respect to psi of that stuff, so d over d psi of f of x e minus 2I pi psi x, which gives us minus 2I pi x f of x e minus 2I pi psi x. We need that thing to be in L1. Okay, we need this to be dominated by some function. So in terms of absolute value, so I want to apply the theorem of derivative of the derivative of parameter dependent integral. So I need this to be dominated by some function that is in L1. Okay, so can we find that? Well, when we don't know about our function, we only know that f is in L1. We need to assume that if x times f of x is in L1, of course that's going to work. It's the same majoration as the one we used earlier. We say that this is going to be in terms of modulus. That's going to be smaller. Well, that's equal to 1. That is just a parameter, and I just need f of x to be in L1. So that is something that we can do if this is in L1, and in that case we can apply the theorem, and that's giving us that this is going to be the integral of the derivative, and so what's remaining? Minus 2I pi integral on R of x f of x e minus 2I pi psi x dx, and this is minus 2I pi. That's the Fourier transform of the x times f of x function. Okay, so that don't forget that equalities like these have two ways. That means that if you're looking for f hat prime of psi, and you know f of x f of x, that's something you can easily calculate. But on the other hand, if you know f and you compute the Fourier transform of f, that's giving you f hat, and you want to know actually what's the Fourier transform of x f of x. Okay, what would be the Fourier transform of x f of x? Well, you know that you knowing f hat, you can compute f hat prime, and from that you can get the Fourier transform of x f of x. Okay, so don't forget that those equalities have two sides. Okay, you might want to get the derivative of the Fourier transform, or you might want to compute the Fourier transform of x f of x. Okay, and well, let's use this. Let's do some application of that formula, for instance. You remember, sorry about this, you remember we had computed the Fourier transform of uh, my gate function. Let's take the simplest gate, the one that is going to be 1 between negative 1 over 2, 1 over 2. Okay, x, and that was the sinus of, so we had obtained the sinus of 2 pi, sorry, let me find that again, the sinus of uh, 2 pi xi a, and a being 1 over 2, that's going to be the sinus of pi xi divided by pi xi. Okay, that's what is called the sinc function. But anyway, so that's the Fourier transform of this function. Now, what can I do with this one? Okay, let's use one of the formulas we have found earlier. Let's try to find the Fourier transform of uh, the gate function applied to, let's say, 1 over 3 times x minus 1 over 2. Okay, so I've got, no, let's even make it a bit harder. Let's say that's 1 over 3 times x minus 1 over 2. Okay, so, and that's going to be a function of psi. So you see, I've got some scaling and some translation. So let's make it correctly one at a time. So first, what is that function? Well, you can compute that directly, or you can use the properties. So let's write it the way we know how to use that. That's, we have to slightly change the way this function is written, or I mean the way the transformations are written, so that we have the scaling of something, okay, and of the variable, and my scaled variable in that case would be x minus 3 over 2. Okay, if I want to apply the scaling to both functions. So you can compute that directly, or you can use the formulas, and you know that you are going to have something like uh, you have to get the shift. So let's see the properties we had. So we have to use, so the scaling, so we were scaling by the 1 over 3, so we're going to have a 3 times the Fourier transform of 3 times psi, and the translation, which means we were translating by 3 over 2, so we're going to have an e minus 2 I pi psi times 3 over 2 in front of that. So that's e minus 2 I pi psi 3 over 2 times divided by a. So a is 1 over 3, so I'm multiplying by a times f hat of psi divided by a, so that's 3 psi. That this is equal to e minus I pi 3 psi times 3 divided by pi xi times the sinus of pi 3 pi xi. Okay, so that's one of the easy property that we could, well, the easy transformation we could find. And then what do we get if I want to find the Fourier transform of the x times pi of x function, 1 over 2 between 1 over 2 and 1 over 2 of x applied to psi. Okay, so what function would that be? That would look like, if that's negative 1 over 2, 1 over 2, this one. Okay, so this function. So I'm just applying the previous formula that tells you that um, the Fourier transform of x times a function is negative 1 over 2 pi times the derivative of the Fourier transform. Okay, so that's going to be minus 1 over 2i pi times the derivative of sinus pi psi over pi psi derivative. Okay, so first thing, I can easily transform my 1 over I by negative 1, negative, negative I over, 2 pi. So with a minus, that's just going to be I over 2 pi times the derivative of what's coming here. So u over v, so that's going to be u prime. So I get pi times the cosine of pi psi times pi psi minus pi times the sinus of psi, pi psi, okay, divided by pi psi. So this is giving me, so I've got at least one, pi psi, sorry, square, of course. So yeah, so I've got 1 pi that is simplifying, so I get I over 2 pi square psi square times pi psi cosine of pi psi time minus sinus of pi psi. Okay, so this is the Fourier transform of x times my gate function, and it's much easier to find using that property than to do it from scratch. Okay, so what other properties do we have? We have our convolution friend back again here. So convolution, um, there's obviously something missing in my formula here. The Fourier series of a convolution is going to be of f convolved with g is going to be the product of the Fourier series, and similarly the Fourier series of a product is going to be the convolution of their Fourier series. So I guess that's not too hard to show, but maybe this is something you can try by yourself. So don't hesitate to pause now or do it later to prove this formula. Okay, so what else do we have? We have few more properties. Again, that's a very good idea for you to work on these properties. So if you apply twice the Fourier series, well, you're going to have not exactly the you have to try that. It's not exactly like the inverse Fourier series is applying again the Fourier series to the Fourier transformation to your Fourier transform. There's some minus sign trailing, so try that. Of You will also get this one. But if you have a complex function, the Fourier series of the conjugate is the conjugate of the Fourier series applied to the opposite of the argument. And okay, and we have, this is what is called the cross identity, but I don't think we're going to use that a lot. Finally, we have the Parseval-Plancherel formula, which is quite important. If you remember last chapter when we were dealing with Fourier series, the Parseval identity was telling you that the L2 norm of a function is the sum, basically the sum of the square of its Fourier series coefficients. Let's see what we have here. First of all, we have to assume that our function are in L2, whereas before we just assumed they were in L1. We just need them to be in L1 in order to apply the Fourier transform. But if ever you've got L2 functions, this is the relation we're going to get. So that first thing tells you, what does it tell you? It just tells you that, sorry, this one, what this integral is actually giving you, so it's not a minus. This integral is actually the scalar product, the inner product that we have defined in L2. F with G, and we have to use the complex one because we have you know that when we're using the Fourier transform, we have actually a complex function. So this is the one you have, but of course if F and G are both real functions, it's not going to change anything. And also very important and similar to the previous Parseval formula that we had, it's that the L2 norm of the function is equal to the L2 norm of its Fourier transform, which is very interesting sometimes. Again, don't forget that this kind of equality are two-sided. What does that mean? For instance, if I ask you to find the L2 norm of that sine of pi xi over pi xi, that would be quite complicated, okay? What would that give you? You want to make the L2 norm of sinus of pi xi divided by pi xi. L2 norm. Take it to the square so that it's easier to compute. That will give you the integral on R of the sine pi xi divided by pi xi square, okay, d xi. This is what you have to compute, and I guess, well, it's not easy to do it. Well, I don't know how to treat that integral when I first look at it, but if you know that you can apply the Parseval-Plancherel formula, you know that this is going to be equal to the L2 norm of your pi function, negative 1 over 2, 1 over 2, okay, of x, the L2 norm of that, which is absolutely trivial to compute. That's just going to be from negative 1 over 2 to 1 over 2, the function that is 1. Okay, and otherwise 0. That's why I reduced my interval of integration to this interval, negative 1 over 2, 1 over 2. And so that's 1. Well, that's actually 1 square, but it's just 1 dx. So that's the constant function 1 on an interval of size 1. So this is equal to 1. So that complicated integral was actually equal to 1. Nice, isn't it? Okay, good.